This is lesson 7.2, part 1, and in this lesson we're going to talk about different types of functions, specifically radical functions, absolute value functions, and piecewise functions. You have seen absolute value functions before if you remember last year. Absolute value, so you have y equals the absolute value of x, and so the absolute value of 0 is 0, the absolute value of 1 is 1, 2 is 2, 3 is 3. And then on the other side, negative 1, the absolute value is positive 1. The absolute value of negative 2 is positive 2, and so it looks like a V shape, so if you remember that. And then if you have y equals, and then we did some with something like that, and now you know a little bit more about inside and how that's going to shift to the right, not the left. And so that would just take that parent function and it would move it to the right 2 places. So you have seen that before, so that part of the lesson will be familiar to you. We've worked with radicals before, but we haven't seen them on a graph necessarily. And then piecewise functions are definitely new. All right, so first of all, let's talk about domain. Remember that domain is where the function is defined. And so when we're starting off talking about radicals, when we talk about the square root, we do have a place where that's a problem. So if you have the square root of a negative number, you have an undefined situation. And so because of that, we have a restricted domain. So this is the first time we've actually had a function that has a restricted domain. And that just means that we can't plug anything we want in for x. There's a certain limit to what we can plug in for x. So radical functions are not defined when the radicand is negative. So if I said the square root of negative 2, it's not defined. And the reason for that is because if we're talking about a graph, this is a real number system graph. It's not a complex number system graph. So in that, there's no definition of that if I try to do square root of negative 2. So the first thing we're going to do is state the domain. So what's the domain of each function? And so the way that we're going to do that is you have to look at the radicand. You have to look at what's underneath there. And you have to think, well, that number has to be greater than or it could be equal to 0. You can take the square root of 0 at 0. You cannot take the square root of anything negative. And so basically that's my domain. So we're going to say my domain is x such that x is greater than or equal to 0, or if you're writing it as an interval, you would say x is an element of the interval from 0 inclusive to infinity. And so either one of those will work. I don't necessarily have a preference. You can just see if there's directions, and if there's not that's specified, then you can do it whichever way you'd like. Okay, for number 2, the radicand this time is x plus 1. So x plus 1 has to be greater than or equal to 0. And then you solve that for x. So x is greater than or equal to negative 1. So you can just do that and write it in set notation, or you could write it as an interval like that. So go ahead and try number 3. So pause the video and try number 3 and see if you can get the right domain. What you should have done is 2x minus 8 is greater than or equal to 0. And we do that every time because what's underneath the radical has to be 0 or higher. And so that's why we set that up like that. So 2x is greater than or equal to 8, which means x is greater than or equal to 4. And so that's going to be my domain. Okay, the last one that we're going to do is right there. Don't worry about that part of it. If I'm just looking for the domain, what's outside doesn't matter. And so I'm only concerned with what's inside because that's the part that potentially would be undefined. So I'm going to say negative 3x plus 15, it has to be greater than or equal to 0. So negative 3x is greater than or equal to negative 15. I'm going to divide by negative 3. Now don't forget that this is an inequality. And in an inequality, when you divide both sides by a negative, remember that you have to flip your sign. If you forget, then you're going to have the wrong answer. So this one, our domain is anything less than or equal to 5. And so you might think, well, that's weird. So does that mean you can plug in a negative? And it does. So let's see how that works. Let's say I'm going to let x equal negative 2. So if I say y is equal to negative square root negative 3 times negative 2 plus 15, is that defined? And so it just means, is that going to be an actual number? And square root of 6 plus 15 is the square root of 21, so this would be negative, and then square root of 21, whatever decimal that is defined. So you could actually put that in your calculator and see. What it also means is it means that anything bigger than 5, like positive 6, would not be defined. So let's try that. If I have y is equal to negative and then the square root, and then we're going to have negative 3 times positive 6 plus 15. That's going to be the square root of negative 18 plus 15. You're going to have the square root of negative 3. This right here is the problem. This does not matter because you can't multiply those together yet because one's inside the radical and one is not. And that's why we did the module about radicals before this, because you have to have worked with them enough to know. So this is our domain right there. So when you're asked to find the domain of a radical, you have to look for where is it going to be true or defined in the real number system. You're not going to be dealing with imaginaries here. Okay, the next thing is we're just going to practice simplifying radical expressions. You've done this before. So you've got what's inside here to the 1/3 power. So remember that that means the third root. And then you've got negative 4, so that's negative 1 times 4, which is 2 times 2, and then a to the third and b to the 9th. So you can write that all out unless you remember exactly what to do. Okay, so the negative 1, the cube root of negative 1, I can do that. It's negative 1 because negative 1 times negative 1 times negative 1 is negative 1. So that comes out. Now the 2's are going to have to stay put. There's not enough of them. You would have to have 3, and I don't have 3. I do have a set of a's. That's going to come out. I have 3 sets of b's, so I'm going to have b times b times b out here. So what I have left under my cube root is going to be 2 times 2, which is 4. So when I write this, it's going to be negative ab to the third power times the cube root of 4. That's my simplified radical. Okay, number 6, notice that we are multiplying because those parentheses are right there next to each other. And so we are going to distribute. So I'm going to have square root 6 times 2 square root 3. And then I'm going to have square root 6, so plus square root 6 times, times negative square root 6. Then I'm going to have 8 square root 3 times 2 square root 3. And unfortunately, I just ran out of room. So then I'm going to have 8 square root 3, so plus 8 square root 3 times negative square root 6. So I'm going to take each of those pieces and simplify. So the first in purple, it's 1 times 2, and then square root of 6 times square root of 3, so square root of 18. I'm going to leave that written down here as 6 times 3 because I'm going to have to simplify it anyway. Okay, the next one is going to be the square root of 6 times negative square root of 6. So I've got 1 times negative 1, so it's going to be negative 1. So actually I'm going to erase that plus and put minus. Square root 6 times square root 6 is just 6. Okay, next I'm going to do the red one. So I'm going to have 8 times 2, so that's 16. Square root 3 times square root of 3 is 3, so 16 times 3. And then 8 square root 3 times negative 1 square root 6. So I'm going to have 8 times 1, so that's going to, negative 1, so it's going to be minus 8. And then square root 3 times square root 6 is square root of 3 times 3 times 2. So, let me rewrite this because it's kind of messy. So I'm going to have 2, and then, actually I'll simplify this while I'm at it. So I'm going to take out a pair of 3, so that's going to come out. So I'm going to have 2 times 3, so that's going to be 6, square root 2, and then I'm going to have minus 6. And then 16 times 3 is 48. And then I'm going to be simplifying that, so I'm going to have a pair of 3's come out. So negative 8 times 3 is minus 24 square root 2. And so then we look at what we can do. So notice that these two have the same radicand. So I'm going to say 6 minus 24, so that's negative 18 square root 2. And then negative 6 plus 48 is positive 42. And so you can leave it like that, or you can write it as 42 minus 18 square root 2. It doesn't really matter. Okay, now for the graphs of radical functions, the parent function is y equals square root x. So just like with any graph, if you're not familiar with it or if you aren't really sure what to do, making a table is a really good idea. Now remember, if I put in negative 1, then I'd be asking you what's the square root of negative 1? Well, it's undefined, so there's nothing there. 0, the square root of 0 is 0. What's the square root of 1? The square root of 2, I could put that, but it's irrational, so I'd have to get a decimal, so I'm going to skip 2. I'm not going to do 2. What about 3? Same thing. What about 4? If I do square root of 4, that's just 2. Now you might be wondering, do I do a positive 2 and a negative 2? The answer is no, because the square root is already in the function. You're not taking the square root of it. You're not inserting that into the problem. So we're just looking for the principal square root, not the positive and the negative. So I can go and graph that. So 0, 0, and then 1, 1, and then I'm going to come over to 4 and up to 2. The next one that's going to have a perfect square is 9. So I'd come over to 9 and I'm going to go up to 3. And then the next one would be 16 and I'd go up to 4. So the way that the parent function looks is like that. And so you'll see that my domain is restricted because there's nothing in this part of the graph. And everything starts at 0 and it goes on forever. Okay, the range is going to be from 0, that's as low as it goes. And it's actually, eventually, if you stick around long enough, this green is going to eventually go higher and higher. And so actually it goes from 0 to infinity. So that's my graph, my parent function, y equals square root x. And the standard form of that, this is, you'll see that this looks a lot like what we've done for quadratics. You've got a, this tells us about our stretch or our compression. You've got h, and that tells us about our horizontal shift. You've got k, which tells us about our vertical shift. The point hk tells us where our initial point is. So in this one, our initial point is 0, 0. So if I take the y equals square root x, if I'm going to write that in standard, or in standard form, it'd be 1 square root x minus 0 plus 0. And so 0, 0 is where I start. There's no stretch. So it's going to go over 1, up 1, over 4, up 2, over 9, up 3, over 16, up 4. So that's how the parent function will go. And so you can tell if there's a stretch or compression the same way we've done it before. If you had a being a negative, then it would reflect. So if I had y equals negative square root x, then what's going to happen is this green graph right here, it's going to be reflected like that. So that would be my graph then, if it was negative. And so that's where when you take the square root of 4 and you get like positive and negative, that's where the negative part is. But it has to be specified. If you just have this, you're not going to be doing both positive and negative. Okay, so number 8, let's graph y equals square root of x minus 4. So first off, we know that our domain, if you think about what we learned in the first part of it, our domain is going to be anything greater than or equal to 4. So we're not even going to get started until we get to this point right here. Everything out here is undefined. There's going to be nothing there. There will be no graph. If we think about our h and our k, then that means that 4, 0 is our point that we're going to get started on, so our initial point. There's no stretch because that's a 1, so I'm going to go over 1, up 1, over 4, up 2, over 9, so 4, which is where we're starting right there, plus 9 is 13, and then I'm going to go up 3. Okay, and so this is going to be my graph. And so we just do it the same way, and that's why the transformations are so important, because they work for any function at all. Okay, go ahead and pause the video, and I want you to try this one. Remember, if you're not positive, you can make a table. So that's always your backup plan in case you don't remember something. Okay, what you hopefully did is notice that there is a reflection. So we're going to be going down like that, okay? There's no horizontal stretch, or sorry, horizontal shift, but there is a vertical shift. So my graph, like if I was going to take my parent function like this, it would be like that, but I'm going to be doing a reflection. And so what's going to happen is it's going to be reflected not like this with a gap. That is, you don't draw them both, but I'm just saying it's not the reflection of that. It's going to be the reflection from that point. So my ordered pair where I'm going to get started is going to be 0, 1. And then I'm going to go over 1, down 1, over 4, down 2. I didn't count that right. Over 9, down 3. over 16 down 4. And this will be my graph. It would be the parent, the y equals negative square root x. That would be like this. And what that's done is it's taken that graph and it's just shifted it up 1. So it starts higher. And so that's what that graph is going to look like. So if I ask you to draw the parent function, it would just be a reflection of that. So it would be, the other half of the parabola. This is the inverse of a parabola, but we're not drawing that. So radical functions, that's how you can tell it's a radical function, is it's like a sideways parabola, but it's only half. Okay, number 10, look at what we have. We have a reflection. What does that mean? What does that mean? So my vertex, or our initial point, will be at positive 4, positive 1. So I'm going to go over to positive 4, positive 1. This will be where I start. Now, if it wasn't a negative right there, I'd be going like that. But there is a negative, so I'm going to be going like that. And so I just need to think about my stretch. There is no stretch. So I'm going to go over 1, down 1, over 4, down 2, over 9, down 3. And I don't have enough room to go over 16, so it's going to go like this. And that's my graph. So all of the things that we've talked about with other types of functions, they apply here as far as the transformation goes. So hopefully that makes it easier for you. Okay, next, graphing the absolute value of x. And so this one is the one I reviewed at the very, very beginning. And so if I take the absolute value of 0, absolute value of 1, absolute value of 2, of 3, of 4, and then the absolute value of negative 1, so y equals the absolute value of negative 1, that would be 1. The absolute value of negative 2, remember it's not the opposite, it's going to be the positive value of it. So you're going to have a slope of positive 1 for part of that graph and a slope of negative 1 for the other part of the graph. And that's your parent function for absolute value. Okay, next we're going to use transformations to graph this. So I'm going to just, in gray, I'm going to do my parent function of the absolute value graph. And then think about what we know about transformations. This is my h, and this is my k. So my vertex will be at positive 1, positive 2. So it's going right and up. This tells me it's a reflection, so it's going to be inverted like that. But it's only going to be half as steep. So instead of going over 1, down 1, we're going to go over 1, down only half. And instead of going over 2, down 2, I'm going to go half of 2, which is 1. So my slope is going to be negative 1/2 and positive 1/2. And that's going to be my graph. Okay, now you don't have to do the parent function unless it says to, but I like to do that especially at the beginning of learning how to do functions because it helps us remember how things are shifted. Okay, you're now ready to go on to the next part of the lesson, which is piecewise functions.